Sorry, the battery died, so I had to change it. So as I was saying, the transfer function of the closed loop is y of s divided by y ref s. So it's just gonna be gc times gp divided by 1 plus gc gp. Okay, so we wanted to make our output closer to our reference, right? Like the desired output. So we had to add a controller. We had to take a measurement of our output. We have to find the error. And now the input to our plant, it's variable based on like whatever happens to this output. Let's say like if this gets bigger than our reference voltage, our error becomes negative. So then the controller makes sure to adjust the input to the plant. The same thing if y gets smaller than y ref. So this is the whole concept of having a feedback and a controller before our plant. This controller can be like can come like in many different forms. There are many different families of controllers. The one that we use in this course is from the family of PID, which is the most common most commonly used controller. So proportional integral derivative, and but there are many other controllers, fuzzy logic controllers, neural network, sliding mode controllers, many different kinds. Model predictive control. So like many different kinds of controllers can be here, but the whole concept is the same. Doesn't matter what kind of controller is. The job of the controller is to sense or to get the error as the input and provides the modified input to our plant. Okay. So I did this one, I did this one. Okay, so many times when you want to measure something, use sensors, right? There are different kinds of sensors. Some of them measure the output itself. Some of them actually measure something related to our output. So it basically, the measurement unit or our sensor itself has a transfer function. One example of that would be, for example, if you want to measure voltage, you might use like a CT, current transfer, or like, sorry, PT, voltage transformer, or like if you want to measure current, you might use a CT, current transformer, to reduce the voltage or the current so that it doesn't damage the rest of our system, right? So we might have a sensor transfer function or a measurement transfer function. Some people use H of S. I'm just going to use GH just to be consistent. Okay, and I'm going to derive the closed loop transfer function for this more general closed loop. So again, y of s, maybe you can pause this and do this yourself if you want. Y of s is equal to gp of s times u of s, right? So if you look at this, we have a transfer function here, u, y. So u itself is E of s times gc of s. Okay, and E itself, so GPS, let me again, like I'm just gonna, let me write all the s's. And E itself is y ref of s minus this thing, right? Let's just call this y of measure. and y measured is y of s times gh, right? So minus y of s times gh of s, and there's a gc here. So okay, it's a little bit messy, but again, let me just take all the y terms to the other side. So here we have a y of s times 1. Let me just again ignore the s's here to make it smaller. 1 plus, here we have y of s times gh times gc times gp. So gc, gp, gh is equal to y ref times gp times gc. gp times gc. And the transfer function is y divided by y ref, right? So y divided by y ref, it's gonna be gp, let me just do it with the order, gc of s times gp of s divided by 1 plus gc of s, gp of s, gh of s. Okay, so this is our closed loop transfer function when we have a sensor here. Okay, so I see that like the effect of that shows here in the denominator. Okay, so that's how we can have a closed loop system with a sensor. Okay, the next thing I want to mention is that how poles and zeros of the transfer function would affect the stability of the system. Okay, so let me just take a small break and then we'll come